In our last class, we have discussed the subsequential limit, and after that, we have proved a theorem that if your sequence is convergent, that every subsequence has the same limit, and some this theorem also important that if you have L is a sequential limit, then every neighborhood of L contains infinitely many point of the sequence. Okay, and after that some problem. Today we will discuss a very important theorem. The name of the theorem is Bolzano-Weierstrass theorem. Okay, so let me write the statement. Sometimes this theorem is almost for state and proof, maybe in 1 plus 5 marks. Okay, so prepare for that. Okay, so what is the statement? Statement is every bounded sequence of real number has a convergent subsequence. Okay, okay, so basically suppose you have a bounded sequence, you can take any example, then you will obviously there you will get at least one convergence sequence. For example, if I consider xn is equal to minus 1 whole to the power n, obviously this is bounded, right? Because minus 1 less or equal to xn less or equal to 1 always. Now can you give an example that it has a convergent subsequence? Obviously, because you know that it has a subsequence x2n which converges to 1 and x2n minus 1 which converges to minus 1. So already this type of example already discussed in the class. Now if you consider xn is equal to suppose 1 by n, is it bounded? Oh sorry, this is convergent. It is bounded. So can you give an example of this of some convergent subsequence? Obviously just consider x2n, x3n, anything if you consider, all are convergent, no issue. But we are interested whenever you know that if your sequence is convergent and every subsequence is convergent, then we are not interested in this type of case. But you know this is not convergent, right? But this theorem says if your sequence is bounded, then obviously this is it has at least one convergent subsequence. Okay, so this is the example. Now you consider xn is equal to just n. Is it bounded? Obviously no. So obviously here you will not find any subsequence which is convergent. Okay, so these are the point. Proof is also important, and this proof is very big. Okay, and you know in this proof we need the nested interval theorem. Already we have discussed in the class. Okay, Cantor's nested interval theorem. Okay, let's prove this. So let xn is a bounded sequence. So bounded means obviously there will be some limit, right? So then there exists a closed and bounded interval I equal to AB such that xn belongs to I for every n, right? Like you can say that xn less or equal to a less or equal to b, that's it. We are writing in terms of interval. Okay. And you know how many element in a sequence? Obviously infinite, right? Now what we'll do, we'll suppose your interval is a to b, this one. Okay, now we'll just divide this interval in two parts. So if you, what is the middle point of this two element? Obviously a plus b by 2, right? Now you know that xn there are infinitely many elements, so obviously one of them in this two sub interval contain infinitely many elements. So sometimes it happen, for example, if you consider 1 by n. Okay, so 1 by n, you know this type of interval contains in between 0 and 1, right? Now if you consider this is 0 and this is 1, and if you divide by these two things, so which interval contains infinitely many elements of this sequence? So obviously this one, because after that 1 by 2, then 1 by 3, all the element will be this side, right? So one of them obviously contain infinitely many elements. Okay, so now let c equal to a plus b by 2. Okay, a plus b by 2, and then consider the sub interval I dash equal to a comma c and I double dash is equal to c comma b. This is clear, right? So then at least one of the interval I dash or I double dash contains infinitely many elements of xn. Okay, one of them will contain, whichever will contain, we will rename that interval. Okay, for example, suppose this is your a, right? This is your b and this is your c. So this is your I dash, this is your I double dash. Now what we will consider, if this one contains infinitely many element, we will rename this is with by a1 and this is 1 by b1. Okay, and now and this interval will rename with I1, which will be by a1 b1. Okay, so this is now our new interval. Now again we will do this type of process, that again we will divide this in two terms. Okay, so suppose this is your next one, c1 will be a1 plus b1 by 2, then whichever will contain infinitely many element, maybe suppose this one. So then we'll rename with this term with a2 and this term with b2. In this way we will continue. Okay, so let's write this infinitely many element. Okay, this one. So let I1 is equal to A1 comma B1 is be such interval that is which contains I1 will be either I dash or I double dash, but we are renaming this term also. Okay, such interval such that I1 will be obviously subset of I, that previous one, right? That I is your earlier one, AV. So obviously this will be inside that. And if we consider the length of I1, what will be this? This will be half of B minus A. Why? Because we what is the initial length? Initial length is B minus A. Now you have divided in two equal parts, so obviously B minus A by 2, right? In this way. Now again you continue same process. So let C1 will be half of A1 plus B1. Okay. Okay, this is A, this is B, this is C. Okay, now after that already we have written. Okay, now you are focusing on whenever you are going, this is your A1, then suppose this is correct. So correct means it contains the infinite element. So you are modifying this. This is your A1, this is your B1. Okay, now you are doing this one by okay. And I1 dash will be your A1 C1 and I1 double dash is your C1 B1. Okay, then at least one of the interval contains infinitely many elements of xn. Let I2 equal to A2 comma B2 be such interval. So this is your I. Here you are getting after that one whichever will be that. This is your actually I1. Now if this is or this is your I2, so next part you will focus on this one, right? So this is your A2, this is your B2. So you can say if your this is contain infinitely many elements, so your A2 will becomes your C1 and B2 will become B1. Okay, so in this way it will become modified in each step. Okay, so I2 be the such interval, and then you have to write the same type of thing. Okay, so I2 will be subset of it is subset of again I1 also. Obviously all are subset of I, and what is the length of I2 will be 1 by 4, right? So in this way we are continuing our step. Okay, continuing in this way. So if you continue in this way, what you will obtain actually? You will get a sequence of interval in, right? And obviously that sequence, there are property that in plus 1 will be subset of in, like I to subset of I1 in this way. And what are the length of in? Length of in will be 1 by, you can see this is your 2 square, right? So 2 to the power n into b minus a in this way. And what is the property, this in property, that in contains infinitely many elements of the sequence, right? So this is the you will get. Okay, let's write. So we obtain a sequence of closed and bounded intervals in such that in plus 1, first one, subset of in for all n belongs to natural number n. Second, in will be 1 by 2 to the power n into b minus a. And therefore limit n tending to infinity, in will be 0. Okay. Third, each in contains infinitely many elements of xn, right? So these are the three property you are getting in in. Okay. Okay, now what is the Cantor's interval? Already we have discussed. Can you recall what is in your Cantor interval theorem? We have discussed the only statement, right, that if you have a closed and bounded sequence interval a and bn, this type of thing, and this is nested, like if this is your a and this is your bn, so n plus 1 bn plus will be inside like somewhere, but overall you can say n plus 1 comma bn plus 1, this type of thing will be subset of that. Okay, so this is like that. Now, and you know, if your length of interval, that is if this is this length, what is the length? Bn minus a, and this is length bn minus 1 by n minus 1. So you can say this length is going to 0 as n tending to infinity. Basically, limit n tending to infinity, bn minus an, this is going to 0. If this two condition is happening, then you can say intersection of all the thing, that bn comma an, if you're doing the intersection for all the thing, this contains precisely one element, right? This is already we have discussed. Okay, now you see here also the structure is all the thing are same, right? This is satisfying this one, sorry, this satisfying this one, because in plus 1 is subset of in. This is also satisfying, and obviously this is nested. So this type of both, all the condition, mainly two condition are satisfying, right? These two condition, this is a part of your Bolzano, but from the first two condition we can apply the Cantor's nested interval. Okay, so by Cantor's theorem on nested interval, there exists a unique point alpha, that theorem says that there exists precisely one point. This one is alpha. This belongs to intersection of I and n is equal to 1 to infinity. Okay, so our claim will be in the proof of Bolzano system, this alpha, there will be some subsequence that which converges to this alpha. Okay, this is our target. Okay, we prove that alpha is a subsequential limit. Okay, this is our target. So let so you know already what you are doing. This is your AB. Next, this will be more smaller, right? After that, you are getting more smaller. Anyway, if you do so all the thing, so alpha is a point, right? Because alpha belongs to all the intersections, so alpha will be such point because it is present all of the interval. Okay, this is you have to consider. Okay, now if you you see already we have proved a theorem that if you consider a number L is a subsequential limit of the xn if and only if every neighborhood of L contains infinitely many points of the sequence xn. Okay, so this is if and only if opposite one also happen, then also you can say this is subsequent. You see the same thing happening here, whatever your alpha is inside, but if you consider any epsilon neighborhood of that, okay, so obviously there will inside that epsilon neighborhood you will get some k for which ik will be inside that, right? So if a, and you know that ik using this third property that each in contains infinitely many elements, so that ik will also contain an infinitely many element. So from there you can say alpha is a subsequential limit. Okay, yeah. So let okay, so let us choose let us choose epsilon greater than 0, then there exists a natural number k such that 0 less than b minus a by 2 to the power k will be less than epsilon. How we can say this type of property? You just think epsilon is any number. This is your choice, you are choosing. So obviously there will be some k for which 0 less than b minus a by 2 to the power k less than epsilon. Why? You can think in this way. If you consider the sequence xn equal to b minus a by 2 to the power n, suppose, okay, where it is converging, obviously it is 0, right? So according, if you use the definition of convergence sequence epsilon 1, that for any epsilon greater than 0 there exists a k such that what modulus of b minus a by 2 to the power n minus 0, this is less than epsilon for all n greater than equal to k, right? This you can say. Forget about mod because this is positive, so from there you are getting some number, this is less than epsilon, right, for all n greater than equal to k. So obviously there exists some k for which this is happening, right? Okay. Fine. Now so you are getting that whatever your epsilon, suppose this is your alpha and this is your alpha, you are getting, this is, I don't know what are the epsilon value, something like that. Okay, now what you are getting, that this epsilon value, this length is your epsilon, right? Now you are getting some k for which this b minus a by 2 to the power k, this is less than epsilon, so it will be like somewhere there, right? So whatever this thing, so from there we can say this is also something like that, b minus a by that is, this one will be alpha minus b minus a by 2 to the power k, this will be your alpha plus b minus a by 2 to the power k, right? This length is this length is this, anyway. Okay, so from there we can say, okay, such that this one, and we can say modulus of ik, this will be less than epsilon. Right. Because in length is 1 by 2 to the power n, so since length of ik is b minus a by 2 to the power k, so this is less than epsilon, so we can write this line. Okay, so since alpha belongs to ik and length of ik is less than epsilon, so ik contains the alpha belongs to ik and ik, length of ik is strictly less than epsilon, and ik, you can say there, then ik will be inside your alpha minus epsilon comma alpha plus epsilon. You can see this picture from here. Okay, so what is your, this is will be your ik, right? Okay, so this is the structure. Maybe you can think, yeah, they are considering actually the length of interval alpha minus epsilon alpha, that is your 2 epsilon, right? And this ik, so it will be better if you consider this thing plus 1, so then it will be more good. Okay, because what is happening whenever you are doing the length of interval, so okay, no issue, yeah, fine, because whenever you are considering the length of integral, so it will be also 2k, right? It will be better if we consider this is epsilon by 2, because what happened, you know, alpha minus epsilon to alpha plus epsilon, this interval length is actually 2 epsilon, so I think this book has some mistake. Okay, so suppose this is your alpha plus epsilon by 2, alpha minus epsilon by 2. So inside that this is happening. Okay, all other point is fine. So this will be epsilon by 2 alpha, this one. Okay, and every neighborhood of, okay, any IGH of alpha contains of xn according to the theorem. Thus alpha is a subsequential limit so therefore there is a subsequence xn k of xn which converges to s to alpha. This completes the proof. Okay, so let's revise the theorem. How you have to, you are considering that you have a sequence xn which is bounded by ab. Now what you are doing next, that you are dividing by 2, that is the midpoint of the interval, and this divide into 2 sub interval equal. So in that sub interval, one of them will contain infinitely many element of xn. That interval you are renaming with a1 b1. Okay, again you are dividing by 2, so again you are getting 2 sub interval, and one of them you will get that contain infinitely many element of xn, and you notice that length of the interval you are getting i1 i2 dot, each time it is dividing by 2. Okay, so in this way if you continue, so you will get a subsequence in where in plus 1 will be subset of in, and length of in will be this. Okay, and each in contains infinitely many element of xn. This is the theorem. Now by Cantor's theorem, you know that you will get a unique precisely one point. That point you are renaming with alpha. Okay, now your job is to prove that alpha is a subsequential limit. Okay, now what you are considering, that we will considering any neighborhood of that. Okay, so basically if precisely alpha minus okay, so this is basically, oh okay, fine. No, I think everything is correct, no issue. Basically what's happened here, we are considering the length is your starting from a and b. Okay, and whenever we are focusing on that alpha, we are focusing like that there will be some alpha minus epsilon, alpha plus epsilon, but this contains it the whole interval, right? So yeah, the book is correct. So you are considering some interval alpha minus epsilon to alpha plus epsilon, so there inside that you will get some subsequence in. After that all the thing will be inside that. Okay, you have seen, if I draw some rough picture, so this is your suppose first one, okay, and you are getting some alpha and you are considering some alpha minus epsilon to alpha plus epsilon. This is like this type of interval, okay. Now suppose you are continuing in this way, so first one maybe this one, after that maybe this one, after that maybe this one. In this way you are getting, right. Now you are considering that interval, that alpha minus epsilon to alpha plus epsilon. You know each of the point will contain alpha. If it is alpha here, so this will be everywhere, right? So obviously you will get some ik for which this interval will be something like here to here or somewhere you will get for every epsilon neighborhood, okay. So this is, it is saying that if you consider any epsilon, so obviously from there you can say that b minus a by 2 to the power k, this type of thing. And this already we I explain you why you will get such k, and you know this is your length of ik, okay. So this is you have. Now since alpha belongs to ik and this is happening, so you can say ik, obviously there will be some k, that for this one your ik will be inside your this alpha minus epsilon to alpha plus epsilon. So like this is the happening, okay. So maybe you are considering this one, if you increase your k, obviously that will be more smaller, right? So inside that you will fit one of the ik, okay. So that's ik also contain finitely many element, right? So that will so from there, using the previous theorem, you can say alpha is a subsequential limit, and this completes the proof, okay. So this is very big theorem. Now we will consider some application type of thing, okay. We will not try to prove any other theorem today, just some application, okay. Okay, there is one more theorem. You have to remember the theorem statement only. So let's complete this. Every sequence of real number has a monotone subsequence. In your theorem only statement is there. If you are interested, so you can focus on the book, okay. So every sequence of real number has a monotone subsequence, okay. You can construct, okay. This monotone means that are less or equal to, okay, not strictly monotone, okay. Okay. Suppose this is your homework. Suppose you have xn is equal to 2n whole to the power minus 1 whole to the power n, okay. So you can write that all the element, okay. Now from that sequence you try to make a monotone subsequence, okay. Like you see how the element looks like. What is the first element? So if you put, I think this will be 1 by 2. What is the next element? So maybe 4. What is the next element? Maybe 1 by 6, right? So in this way you will get, so you have to make some more subsequence. So obviously you will get maybe this and this in this way, and we will get one more this. Okay, so there EJ has a subsequence. Okay, okay. So this is your one problem, that xn equal to 1 plus half plus 1/3 dot 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 in this way. Prove that xn is divergent. Whenever we will discuss the series, you will get more idea about this type of series, but still whenever you have not completed the series, so you have to think how to do this type of problem. Okay, so what we will do, we'll rewrite this one like 1 plus half, okay, plus 1/3 plus 1/4, okay, plus 1/5 plus 1/6 plus 1/7 1 by 8, and in this way we'll make this type of. So this is just ignore it. This is your first element, this is you have 2 element, next you have 4 element, in the next bracket you will get 8 element. In this way we will trying to make. So you see this is your 1 plus half. You see we can write 1 by 3 is it is greater than 1 by 4, right? So instead of that we are trying to write this one. Okay, here also we are writing 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8, because you know 1 by 5 is greater than 1 by 8, 1 by 6 also greater than 1 by 8, so we can write this way, right? You just think, and so on. So after that this line you can write 1 plus, this is half, this is also half, right? Okay, I am writing the last term is your 1 by 2 to the power n. So you can see this is your 2, this is your 2 square, this is your 2 cube. In this you are considering this type of bracket, right? Okay, and what is the last term also we can write on it. Okay, if you are confused why this element, you just one minute, sorry, here we are not writing this element, this line will be in the previous one. Right, everywhere we are writing 1 by 2 to the power n. So if you add in this way, obviously everywhere you will get half, right? You just check how many n times, so you are getting 1 plus n by 2. So you are getting basically xn is greater than 1 plus n by 2, and this is converging to infinity, right, as n tending to infinity. So you can say xn is divergent. Okay, okay, your task is homework 2, if your xn is 1 plus 1 by 1 factorial plus 1 by 2 factorial dot 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 n factorial, proof xn is increasing and bounded above. I am stop the class here. We'll take the Cauchy criteria in your next class. Okay, bye.